Hello, good morning. Hello, am I audible?
Yes, sir.
Okay, good morning and welcome to our lecture on advanced power electronics. We take a review what we done last time. Last time we just introduced the multi-level inverters and a classification is based on two things. One is number of pole voltage levels and other is the topology. So based on a number of levels, here we have seen that we are discussing the voltage VAO. A is the one leg output and O is the center point of DC link. And here this diagram we have seen that VAO has a two levels. When switch is upper side, voltage level VAO is plus VDC by 2, and when the switch is at lower position, our VAO will be a minus VDC by 2. In case of three level, we are having a VAO, we are having a three positions of the switch. Let us know the switch is at upper side, then we get a plus VDC by 2. Switch is at middle, here we get O point is shorted with A, VAO is 0, and when the switch is at lower side, our output voltage is minus VDC by 2. So here we are having a three levels, plus VDC by 2, 0 and minus VDC by 2. Similar we continue for a 5 level, and here we have seen that with respect to center point of DC, we are having a VAO. If it is connected to the upper point here, then we are getting the, with respect to this, VDC by 4 plus VDC by 4. So it will be a VDC by 2. So whenever switch is at first position, you can call it, our VAO will be plus VDC by 2. When it is second position, our VAO will be a VDC by 4. Third position, it will be 0. Then fourth position, which is a minus VDC by 4. And fifth position, it will be minus VDC by 2. So these are the levels, what we obtain two level, minus VDC by 2 and plus VDC by 2. 3 level, minus VDC by 2, 0, plus VDC by 2. 5 level, minus VDC by 4, minus VDC by 2, 0, plus VDC by 4 and VDC by 2. This is a with a pole voltages, and pole voltage we measure with respect to a center of DC supply. Here pole voltage levels we can also with respect to the negative DC rail, and if you hear two level negative DC rail, we also, when the switch is at upper side we get a VDC, and when the switch is at lower side, 0. So in this case of two level we get a 0 and VDC. In case of three level we get a VDC by 2 and 0. Okay, so this will be a 0 VDC by 2 and VDC. 5 level, 0 VDC by 4, VDC by 2, 3 VDC by 4 and VDC. So we adopt the second convention here. Both are correct. Now let us here particularly another classification based on the topology, a circuit configuration, and we are having three uh, topologies. First is called as a neutral point clamped. Neutral point clamped, in short we can NPC, or it is also called as a diode clamped multi-level inverter, NPC or diode clamped multi-level inverter. Second circuit configuration is flying capacitor multi-level inverter, and third is cascaded H bridge multi-level inverter. In that case, single phase as well as three phase options are available. Okay, so now this is the circuit we are going for, the neutral point clamped MLI or diode clamped MLI, and this is a three phase three level. We are having a three phase means normally inverters we are having a three phase because our loads are the three phase loads, so we are having a three phase, and here number of levels we are having for a three levels. Okay, and already we have discussed three levels with respect to center point O. We are having a plus VDC by 2 0 and minus VDC by 2 or A. Now here we have seen that one leg is consisting of four fully controlled devices. One leg is four fully controlled devices, and we take output from the after two devices. Second leg is similar and third leg is similar. Whereas we divide the DC link, this is our supply is available. And how we divide the DC link? One option available is we can divide the DC link with the capacitors. We use a equal value of capacitors. Depending upon load requirement, we can find out the value of capacitors. So we are using the two capacitors, so that a capacitor 1 will have voltage will be half of the VDC, so it will be a VDC by 2, and another capacitor is also VDC by 2. And the center point, if it's our that is a neutral point, you can clamp through a diode. These diodes we can call as a clamping point, and they are connected to in between the switch S1 and S2. In between that is connected. Similarly, S1 dash and S2 dash, another diode is connected. Similar for the second leg. So this O point is connected to the diodes here. Diodes. It is not connected to the output. Okay, so O point is connected at these points through a diode. So in all, this circuit requires 12 IGBTs. Okay, circuit requires each leg is 4. A number of legs are 3, and hence this circuit configuration requires a 12 IGBTs. Then we require two capacitors for splitting of the DC link, and we require 6 clamping diodes, 2 per leg. We require 6 clamping diodes. So these are the circuit components required. Here one particular, you are given the names S1, S2, and here S1 we can call as S1 dash. That is a here we can call as a S1 and S1 star or S1 dash. They form a one pair. A complementary pair we call as a S1 and S1 dash. Complementary pair, it means that if S1 is on, S1 star or S1 dash will be off. If S1 dash is on, S1 will be off. So out of S1 and S1 star, one device will be on, one will be off. That is the meaning of a complementary pair. So here we are having the upper device and third number device. So S1 and S1 star or S1 dash, these two devices will form a complementary pair. Similarly, here S2 and S2 dash will form a complementary pair. S2 and S2 dash will be, we are having a complementary pair. And in that case, so how many switching signal we have to generate? Okay, we have to generate almost 6 switching signals. If we are knowing the switching signal S1 we generate, S2 we generate for first leg, similarly the second leg and third leg, and correspondingly another 6 will be just inversion of this. So now how we get the voltage levels, various voltage levels we can see here. We consider for the one leg. Let us we consider the one leg of this just to get, and here we have seen that this is C1 and C2 capacitors, and we split up the VDC C1 and C2, and here let us assume that these upper two are on. Let us assume that upper two are on. So A point is connected to a here at upper, and it will be AO. The voltage appearing across the load will be of the C1, so it will be a plus VDC by 2 with respect to this. So here when S1 and S2, these upper two devices are on, it means that S1 star and S2 star, these two are off. So S1 and S2 are on, and S1 star and S2 star, these are off. Then we get VAO, that is pole voltage VAO is equal to plus VDC by 2. Now whenever we are switching on S2 and S1 dash or S1 star, these two devices, S2 and S1 star are on, then our voltage, so let us assume that through this positive current, let us assume that through this it will be connected to the, so O point is connected to A when current is positive through this. When current is negative through the S1 star, it will be connected to this. So it means that whether load current may be a positive or negative, depending upon that, we have seen that a particularly one device will get a path and O point is connected to the A, and so we'll get the VAO node voltage is 0, and the condition will be S2 and S1 star will be on, and when S2 is on means S2 star is off and S1 is off, S1 and S2 star is off. Now whenever lower two devices S1 star and S2 star are on, it means that upper two are off, and where lower two are on, it means that A point is connected to the negative rail. With respect to O point, the voltage will be a VDC by 2. So here we have shown the various switch conditions for getting the voltage VDC by 2, 0 and minus VDC by 2. Okay, we get this. Now how will be the currents? Okay, whenever we are going for now next we are going for, let us assume that S1 and S2 are on. We are considering one leg, same is valid for the other legs, and let us assume that these upper two devices are on. Upper two devices are on, and let us assume that our current is positive. Load current positive is from A to O, that, and this O point and this O point is one and same. To avoid circuit complexity, I have shown it ground here and shown it ground here. So let us assume that load is connected with respect to a point O. And now whenever S1 and S2 are on and current is positive, so current will start from this. Who will supply this current? When S1 and S2 are on, load current will be supplied by the capacitor, upper capacitor C1. C1 will supply. So current from this, it will through S1, S2, and then it goes to the load and this. Whereas whenever this switch is on, but our current is negative, maybe a load conditions, then the negative current will flow like this from the load. Okay, it will through the diodes now. Path will be through the diodes, and then it will be going back to here. Okay, through this it will come to here. So this will be a path, particularly when current is negative. Current is negative, then anti-parallel diodes will conduct, and when current is positive, we see that our S1 and S2 devices will conduct. So when current is positive, we are shown with a red diagram. So from capacitor, it will go to the S1, S2, then load, and it comes back to the capacitor. C1 will supply the power. C1 will discharge when the nature of load current is shown by the red. And if you see here, our current direction is reverse. Load may be RL or this. And in that case, our current is negative. In that case, the current will flow from load through these diodes and it will charge the capacitors. So this is the case how when our switch S1 and S2 are on, and when S1 and S2 are on, it means that S1 star and S2 star are off. Okay, so these clamping diodes will not take a part at all in this case. So this is the one level when S1 and S2 are on. Now let us go lower. Let us assume that lower two are on. Lower two are on means upper two are off. And now lower two are on. So now this is the positive of the capacitor. It comes here. Okay, this from this to the load and this through the switches S1 star and S2 star, a circuit will complete. When the load current is okay with respect to particularly this nature diagram we are shown. If current is reversed, then how will be our direction of current? If current is reverse, means current is now flowing like this. It will come to the battery here. Okay, reverse direction current through this. Then we have seen it here. It will flow through these two diodes and then go back to the load, and so this will be a current, another current, when reverse current you can call it, when diodes are conducting. Okay, so and here we have seen that our VAO, particularly we are getting is minus VDC by 2. So we have shown it here how we obtain a plus VDC, because a point is connected to here upper this particular portion, a point is connected, and that's why upper capacitor is coming across the load, so it is plus VDC by 2. Here lower capacitor is coming across the load, but in the reverse polarity way, so we are getting the output is minus VDC by 2. Now let us go for our third level. That will be a, what we are having is, this is our S1 star and S2 are on. This is S2 is on and S1 star. Middle two devices are on. Middle two devices are on, and in that case we have shown it here a red. Okay, now this point, let us assume that load is having a positive current. Okay, this A to 0. So how that positive current from this O point through this clamping diode. So current will be from O point through the clamping diode to this, that go to a switch S2 in this direction, through a switch S2, and then to the load, and it completes the path. Whereas whenever current is opposite direction, negative current we can call it, then here we have shown it here, our switch S1 star is on. So path of current we shown with the blue, from the load it goes to the S1 star, and from S1 star through a clamping diode it goes back. And here we have seen that point O and point A are connected together, and hence our VAO will be a 0. So we have shown the switching for obtaining VAO plus VDC by 2, VAO minus VDC by 2, and VAO will be a 0. So any question? So this is okay. How we get output once we are knowing this? So VAO, VBO, VCO, then we can get a from VAN, VBN, VCN. And once we are getting VAN, VBN, VCN, we can find out the space vector as well as the line voltages. So any question? Am I audible?
Yes, sir.
Yes, sir.
Any doubt? We are discussing the three-level inverter, diode clamped multi-level inverter, three-level. Number of devices are 12, and we require 6 clamping diodes and 2 capacitors for splitting the DC link. And we have seen that a complete concept of the complementary pair. What is mean by the concept of complementary pair? So S1 and S1 star, they are complement. S2 and S2 star, they are complement. Out of these S1 and S1 star, first and third devices, any one will be on. Similarly, S2 and S2 star, out of that, only one device will be on. And that concept we can call as a complementary pair. So here, each leg we are having a 2 complementary pairs. So totally we are having a 6 complementary pairs in this. Now we want to increase the number of levels. So same concept, we want to go for a 5 level. Okay. So now we are just showing the one leg of the 5 level inverter. It is a diode clamped or the neutral point clamped 5 level. So here number of levels in the output voltage we can obtain will be the 5. And here for that again our point O. So here, so this is our O point. With respect to this, we are measuring the voltages. And what are the various values we are knowing? What are the 5 levels of VAO? And the switch conditions, we are already knowing this. So what are the possible, can you just tell me what are the voltage levels, 5 voltage levels in this case? VAO, what are the 5 voltage levels? Anybody can unmute and tell.
Plus minus VDC by 2, plus minus VDC by 4, and 0.
0, correct. So these are the five uh, particularly switching voltage levels we can obtain, and we are already knowing the concept of complementary pairs. So this S1, and correspondingly we are having a S1 star, S1 and S1 star. These are the complementary pairs. Similarly, we are having a S2 and S2 star, S3 and S3 star. So I'll just use the S2 and S2 star, S3 and S3 star, S4 and S4 star. So we are having a four complementary pairs. So each leg we are having 8 devices. Is it right? Each leg we are having a 8 devices. So we require how many? 24 devices we require. And here this clamping diodes, if you see it here, so one particular first, particularly S1 and S1 star, emitter of this S1 and emitter of S1 star is connected through the diodes. And if you see here, we have shown it four diodes. Okay. So purpose here is that each diode voltage rating is same. So depending upon how much voltage is available, blocking voltage, based on that we are use this. Okay, so here voltage available is more, so and here is less, so one diode and the three diodes. Okay, so here our assumption is blocking voltage rating of each diode is the same. So here how many blocking diodes per leg are required? We have seen that here 12 blocking diodes are required. Each part here we can require a 4, another 4 and 4. And we have seen the circuit. And here we have seen that our DC link is now split up into a 4. DC voltage we are split up into a 4. So each is having a VDC by 4. Each capacitor is having a voltage will be equal to VDC by 4. Each capacitor voltage is a VDC by 4. So this VDC by 4, VDC by 2, minus VDC by 4 and minus VDC by 2 at this point. We have shown it is upper point with respect to O is plus VDC by 2. Then middle point with respect to center, this will be plus VDC by 4. With respect to this point here, we can have minus VDC by 4 and then minus VDC by 2. Okay. So this is the particularly we require four capacitors, so we can split up the DC link into a VDC by 4. Each capacitor is carrying the voltage equal to a VDC by 4. And now we are having a VAO. Okay. And now how we can get the which devices will be, again here complementary pair is there. If upper 4 are on and lower 4 are off, let us assume that, so we can get it here plus VDC by 2. When we can get it a plus VDC by 2? So here 5 levels are there. So this is a case I am showing it here: S1, S2, S3, S4. Upper 5 are, sorry, upper 4 are on. Upper 4 devices are on. Then this A point is coming at the positive DC rail, and positive current it will come from this point, positive rail, and through these switches S1, S2, S3, S4 it comes to the A, and from that it goes to the load. So these two capacitors will supply the energy whenever S1, S2, S3, S4 are on. This C1 and C2 will supply the energy. And when, let us assume that when the load current is, when load current is opposite direction, in that case what will happen? This will be a load current, it will flow through, now the current will flow through the diodes. Okay, anti-parallel diodes. Through this it will goes to this, and here charging of capacitor particularly will take place. So this is a first level, what we can call it, when upper 4 devices are on, S1, S2, S3, S4. These 4 devices are on, S1, S2, S3, S4 are on. Now we get a VAO will be plus VDC by 2. and then lower 4, S1 star, S2 star, S3 star, and S4 star are off. And we have seen how our positive current, load current, will flow through the switches S1, S2, S3, S4, and negative current, you can call it, it will flow through the feedback diodes and charging of the capacitor. This is a plus VDC by 2 level, and we can go immediately minus VDC by 2 level. When we get a minus VDC by 2, lower 4 are on. When lower 4 are on, devices are on, and then A point will become to a negative range with respect to O. Now here we have seen that C3 and C4, they will provide the energy, and we have seen that the path of current, so C1 or C3 positive is grounded, it comes from here, it will come to this from the load to the point A. From A it will go S1 star, S2 star, S3 star, S4 star, and from this it will be going to the capacitor. And whenever our current is negative, whenever current is negative, in that case current is reversed, and in that case particularly we have seen it here, a current particularly will be opposite direction, so it will be like this. So current will be downward direction through these capacitors, then through these diodes, anti-parallel diodes, and then it will be going to the load, and this will be again going to this. So this will be coming at point O. So this is our what red waveform, we show the negative current and we show the positive current, and again our this point A point is come to the here, it is a negative rail. So our, and these two capacitors C3 and C4, these two capacitors C3 and C4 will supply the energy or take the energy, what we can call it, and that's why our voltage level will be a minus VDC by 2. Now let us go for circuit for plus VDC by 4. So what will be our switching? So here now S1 is off, S2, S3, S4. As S1 is off, S1 star will be on. So from second, third, fourth, and fifth devices, these are on. S2, S3, S4, and S1 star are on. And now here, how is the positive current? So red waveform we have shown it here. So C2 here, this C2 will supply this. From C2 we come to a clamping diode. This will be through clamping diode, through S2, then S3, then S4, and then goes to this. Again it will go. So red waveform will show the positive current, and this positive current will flow through the clamping diode from a C2 capacitor to clamping diode to S2, S3, S4 to the load point A, and then from O it will goes to this. And here in that case, who will supply the energy? We say that our C2 will supply the energy. Plus VDC by 4, C2 will supply the energy. Whereas load is opposite direction. If the load is opposite direction, load current is opposite direction, that will be shown with a blue color. And in that case, our S1 star will be on. And through these three clamping diode, a charging of what we can capacitor will take. A negative current, we say the charging of capacitor C2, a positive current, a discharging of capacitor C2. So this is the level we get. So voltage appearing across the VAO will be a voltage across the capacitor C2. That is a VAO is plus VDC by 4. In that S2, S3, S4, S1 star are on, and S1, S2 star, S3 star, and S4 star are off. Now go for minus VDC by 4. In case of minus VDC by 4, what is happening? Now S4, S1, S2, S3. So first S1, S2, S3 are off. So S4 onwards. Okay, S4 is on, S1 star is on, S2 is on, and S3 is on. As S4 is on, S4 dash is off. And now for a positive current, here it will be minus VDC by 4. So particular VO is minus VDC by 4, and capacitor C3 is provide the energy. Okay, C3 will be provided the energy. When load current related C3, it will come to here. Okay, so this is a from C2. Okay, yes. Okay, from this C3, you see it will be coming it here, and then will 1 minute. So here, with respect to this, so here we come it here. So this is our positive. So positive, or we can take a positive current here. So let us assume that here a positive current this direction, and so here this will be from this negative of this, let us assume, and this diodes D3 will conduct through this, it will come to a S4, and through this it will be a positive current. And opposite current how will be from this A to this, and then it will flow through S3, S1 star, S2 star, S3 star, and then it will come to this point, and okay, it will be goes to this VDC by 4. So our voltage level we obtain will be a VDC by 4, and S4 on devices are S4, S1 star, S2 star, and S3 star. So this will be a minus VDC by 4. And how we get the zero voltage level? So for getting a zero voltage level, S3, S4, S1 star, and S2 star are on. Okay, so S3 and S4 are on, S1 star and S2 star are on. So here in this case, zero level means A and O are shorted. Let us for a positive current, what will happen? This particularly this D1 and this through S3 and S4, A point is connected to O. When your current is negative, A point is connected through S1 star and S2 star, okay, to D2 dash, and then it is this. So we have shown it here. Okay, so S3 and S4 are on for one direction of current, S1 star and S2 star are other for direction of current, and in that case, point A of the load and the center point of DC, they will be a shorted, and our VAO will be a 0. So in this fashion, we are getting the 5 voltage levels: plus VDC by 2, minus VDC by 2, plus VDC by 4, minus VDC by 4, and 0. And now this is what switch position we have just shown it here. If you see it here, plus VDC by 2, these 4 are on, S1, S2, S3, upper 4 devices are, lower 3 are off. And plus VDC by 4, S1 is off, and S1 star will become on. Now 0, S1, S2 are off, S3, S4 are on, and as S1, S2 are off, S1 star and S2 star are on. So it is you can see the very simple which devices will be on. We have shown the table particularly for getting plus VDC by 2, plus VDC by 4, 0, minus VDC by 4, and minus VDC by 2. Now there is one question. Okay, with this, now you should be able to answer. Suppose we are in a 3-level inverter or a 5-level inverter, whatever we discuss, can it will be operated as a 2-level inverter. Question is, this is a 3-level inverter. Can you operate as a 2-level inverter? Am I audible?
Yes, sir.
So can you operate a 3-level or 5-level multi-level inverter? Can it make as a 2-level inverter?
Yes, sir. We can just neglect the third operation, zero condition.
So, okay, so we can avoid only in case of 3-level, we can go for plus VDC and minus VDC. We don't go for 0 level. Is it right? So whenever we can have just upper 2, we can make simultaneously on, lower 2 simultaneously on. We don't go for 0 level. So we can use only a plus VDC by 2 level and a minus VDC by 2 level. Then a 3 level can be operated as a 2-level inverter. What about 5-level inverter? Can the 5-level inverter be work as a 2-level inverter? Can 5-level inverter we can work as 2-level inverter?
Yes, sir. We can just use two
Yes,
conditions.
so only
Plus
again here we have to use plus VDC by 2 and minus VDC by 2. It means that we have to switch on S1, S2, S3, S4. You can make it as a one switch, simultaneously on and off. It means that you can make as a one switch. Similarly, S1 star, S2 star, S3 star, and S4 star, you make as a one switch. So any multi-level inverter can be operated as a two-level inverter. Okay, a 5 level, 7 level, 3 level, any higher level multi-level inverter, it is possible to make it as a operation as a basic or two-level inverter. So this was the question. Okay, is it clear? Now any doubts regarding the operation of this 3 level and 5 level diode clamped multi-level inverter? Any doubt, any question?
No, sir.
Is it any doubt? Okay.
No, sir.
Now let us go for switching. Now we can go for a space vector diagram. So we can go for this table, we can commit or we can just discuss here. Particularly we have seen it a two-level inverter. So for our two-level inverter, how many switching states of the inverter? Two-level inverter, we have seen that 8 switching states. 6 are active and 2 are inactive. And for two-level inverter, number of switching states, level raise leg, that formula we can use for a number of switching states. Level, it is a two level, legs are 3, so two level inverter, 2 raised to 3 8. Now if the 3 level and 3 phases, 3 level and number of legs are 3, so 3 level inverter, 3 raised 3, we are having a 27 switching states. A 5 level inverter, we are having a 3 legs and 5 levels, so 5 raised 3, so 125. So this way just you can use any 4, you can find out the switching states of the inverter. Switching states will be given by level, raise, number of legs in the inverter, or it is normally we are leg is 3. Okay, normally we are going for our inverter is a 3-phase inverter, so leg will be equal to number of legs will be a 3. Number of legs will be a 3 here, and levels a 2 level, 3 level, 5 level. So legs are 3, so 2 raised to 3. 2 level inverter, we are having 8 switching states. 3 level inverter, 3 raised to 3, 27. 5 level inverter, 5 raised to 3. Similarly, we can go for 7 level, 7 raised to 3. So you can find out 7 multiplied by 7. So how many states we are having. So this will be a number of switching states for higher levels. We can get it. Okay. So here this is a switching states. Now how to represent the pole voltages. When our level is plus VDC by 2. In case of two level, we are use the letters as 0 and 1, 1 and 0. Is it right? In case of two level, we use the letter, we use the numbers here, binary numbers, we can call it 0 and 1 to represent the switching state. Because we are having a one leg, two devices are there. When upper device is on, we can call it as a 1, and when lower device is on, we can call it as a 0. Either in leg upper or the lower device will be on. So we are having in terms of this, we represent in case of two level, we represent the switching term in case in with the help of 0 and 1. But in case of this, particularly we are going for 3 level inverter, and in case of 3 level inverter, we require 3 switching. We are having 3 levels pole voltages, and whenever plus VDC by 2, whenever our voltage level VAO or pole voltage level, when our pole voltage level is plus VDC by 2 or upper 2 are on, then we can represent it as a A. In earlier case we are using 1, here we can use as a A. And when our pole voltage is 0, means middle two devices are on. So here I have to also put a diagram of this, but okay, I have forgotten to keep it here, a two-level inverter. So whenever upper two are on, we can call as A. When middle two, S2 and S1 star are on, we can make it 0 or O you can call it. And when a lower two are on, we can call it as a B. So we use the letter A, O, B. Okay. So we use here three letters to represent the states of the three-level inverter. So upper two switches are on. Okay, we can represent as a. When middle two are on, we can call it will be a 0, and when lower two are on, we can call as a B. So our switching states we can represent in terms of letter A, O, B. Okay, A, O, B. And here, what is the correspondence, particularly with two level? A two level correspondence, one will be a corresponding to a A. Okay, one will be a, this is for two level. So whatever one in case of two level, one in case of two level will be represented as A, and 0 in case of two level is represented as a B. Okay, B. And now here, let us, we are having this. So we are having, if you see it here, 0, 0, 0. Okay, that will be our voltage level, two level. Okay, this will be a two level, 0, 0, 0. And if you represent in case of three level, 0 we represent with B, B, B. Okay, one we represent A, 0 we represent B. And if you see that, we have shown the here 8 switching states of two level inverter. 8 switching states of the two level inverter. Okay, 0, 0, 0, 1, 1, 1, all these we are having, and 1 you make it equal to A, 0 you make it equal to B, and then we are having these switching states for a three level inverter. We are getting how many switching states for this inverter? We are having a 27, and these 8 are common. Okay, we can call it whatever two level and three level. We have just shown it here. 0 you replace with B, then 1 we replace with A, and you are knowing already V1, V2, V3, V5, V6, V7, all these. Okay, and correspondingly, so these states are the common for a two level and a three level. Now before going to that, how is our space vector diagram? Now our procedure is simple. Okay, same procedure for two level, we can use it here for finding out the space vector for a three level inverter. The space vector for three level inverter, how we find out? So one switching state is given. Okay, one switching state is given. So now let us assume that our switching state is AOB. Let us, our switching state is AOB. We first leg A means which, what is our VAO here? First leg. So here what is our VAO? This A means upper device is on. So VAO will be how much?
VDC by 2.
So plus VDC by 2 we are having. Then second leg 0 or O, it means that VBO is how much? VBO is 0, is it right? Because 3 we are having switching states, 3 levels plus VDC by 2, and 0, this O corresponds to a VBO will be equal to 0. And what is the value of VCO? VCO will be equal to, here B letter corresponds to lower two devices are on. Third leg lower two are on. Middle leg middle two are on. We have taken any random state. Okay, VCO will be now a minus VDC by 2. It will be a minus VDC by 2. So whatever switching state is given, okay, for that find out VAO, VBO, VCO. And once you know the VAO, VBO, VCO, we can, using the matrix we are already studied for two level, we find out VAN, VBN, CN. Once we know the VAN, VBN, VCN, we can find out the uh, Vx and Vy. And once you know the Vx and Vy, we can find out the space vector. The procedure is same. Already we have done for two levels. Same, we can use it. Only thing that in case of two level, only two values for VAO, VBO, VCO. It will be plus VDC by 2 or minus VDC by 2. In case of three level, we are having either plus VDC by 2, minus VDC by 2 or 0. Now let us go for the exercise. That is what we are here, particularly AOB state. Let us take the switching space vector. We find out for a switching state is AOB. So here A means VAO is plus VDC by 2. VAO is plus VDC by 2 when it is for the A. O means VBO is 0. O means VBO is 0. And B means VCO is minus VDC by 2. Okay, we're taken in a random state here. So once with the switching state is given it here, AOB, then we can use this. We can use the relationship between the node voltages or pole voltages and the phase voltages. We can use the relationship between the VAO, VBO, VCO and VAN, VBN, VCN. This matrix you can use it, put the values of VAO, VBO, VCO, compute this, and then we get the VAN, VBN, VCN. And VAN, if you just put the values here, plus VDC by 2, VBN is 0, VCN is minus VDC by 2. And once we go the 3, then we can have another matrix. That matrix I have not shown it here, okay? So that matrix I'll just go back and show you. So once we are doing the VAN, VBN, VCN, so here VAN, VBN, VCN are known. And then 1 minus 0.5 minus 0.5, 0, 0.866 minus 0.86. A and B and Cn are known. Then you can get the Vx and Vy. And once Vx and Vy is known, you get a space vector Vs will be square root of Vx square plus Vy square. And angle will be a tan inverse of Vy by Vx. So with this, so this will be same procedure. My point to trace is the same procedure we can use for finding out the Vx and Vy. Okay, so sorry. So we 1 minute. Once we know this, okay, so we get this, and then after that, already we are here. Okay, we are not seeing it here. So Vx and Vy, we can find out Van, Vbn, Vcn. You put it the values. Vx will come out to be 0.75 VDC. Vy is this, and then we can get the magnitude of space vector is 0.866 VDC, and angle it will come out to be a 30 degrees. Okay, a phase of Vs will be a 30 degrees. And now here, so this is we can represent here. So this is a diagram. If you see it here, it is a hexagon. Okay, so I will just use the pen here. So I'll just get these points. If you see the corner points or this hexagon points, this will be same for 2 level and the 3 level. Is it right? 2 level and 3 level. These are the common at this. Okay, so hexagon, so space vector diagram for any multi-level inverter or 2-level inverter is in the form of a hexagon only. Okay, it will be in the form of hexagon only. So this is our space vector diagram, particularly for a 3-level. What we have to do here, first I will tell. So this is a VDC link, is it right? This magnitude, each side of the space vector diagram will be equal to VDC. And what is meaning of VDC? VDC is the input voltage to the inverter. VDC. So length of, if you go for 2-level inverter, so length of this particularly hexagon, side of hexagon will be always equal to VDC. And here we have seen that our levels are 0.5 VDC, 0 are also there. So here, so once you get the hexagon, this particularly VDC you divide into half, VDC by 2 and VDC by 2. So you get the points. So this hexagon, each side you divide it by 2, get the center of this. Okay, and then you make the lines parallel to the sides of the hexagon. You make the lines parallel to the sides of hexagon, and then you will get this diagram. So this is for a 3-level. What you can divide the DC link into a VDC into 2. If it is a 5-level, what we have to do? We have to divide the DC link into 4 equal and make the diagram. So making the diagram for a space vector is very simple. For 3-level, this DC voltage you have to divide into the 2. Is it? Otherwise, I will show it here once again. So this is our voltage magnitude will be how much? Each side of the hexagon will be equal to how much magnitude? Each side of the hexagon will be equal to VDC. Each side. So very simple logic is 3-level means -1. So you can divide the DC link, or you can divide the DC into 2. So this will be, I have divided, this will be half VDC by 2, VDC by each. Okay, side of hexagon you divide it by VDC by 2, VDC by 2, get the center point of each. Okay, you can get it. And then connect, you can make the lines, okay, through these lines parallel to the sides of the hexagon, and correspondingly you will get the space vector diagram. And whatever crossing points, if you get it here, any crossing, 2 lines are crossing, that crossing points is nothing but the switching states of the inverter, switching states of the 2-level inverter. And now here, so if you find out at particular cases, if you see it here, I will just show it here. This particular, if you see this point where the same space vector we can obtain by 2 different switchings. Here also we obtain the same space vector. This space vector we can obtain with the 2. So if you are having the inner hexagon, if you look at here, we are having 2 hexagons. If you see it with respect to the center, we are having the 2 hexagon. One is outer hexagon, where each crossing will have a unique switching state. But here, inner hexagon, if you see it here, this is the inner hexagon, where each crossing we are represented, each switching state is represented here. It will be shown as BOB or BAO something here, or AAO or OOB something. So each switching state here, this switching state may be represented by 2 set of switching. Similarly here 2 set of switching. So inner 6 we are having is the 12 switching states. Inner 6 is we are having a 12 switching states. At center we are having 3 null vectors. Here we are having a 3 null vectors, and these 3 null vectors are, one is AAA, BBB, and 0OOO. These are 3 we are having at the center. 3 null vectors. Then this is a 12, 6 multiplied by 2, that will be a inner hexagon, and 12 at the outer hexagon. We are having 12 at the outer one. 12 plus 12 plus 3. So we are having 27 switching states of this inverter, and the space vector diagram is like this. So is it clear how to draw the space vector diagram for any multi-level inverter? Is it clear? What are the steps? So first you draw the hexagon. First you draw the hexagon, whatever may be your number of levels of the inverter, maybe 3 level, 5 level, whatever it may be. So first thing is you draw the hexagon. And you are knowing each side of the hexagon will be equal to VDC. Each side of the hexagon is VDC. Each side of the hexagon is VDC. If 3 level, you divide into 2. If it is 5 level, divide this VDC into 4. All this, okay. So on each side, you divide this VDC into a 4 for 5 level, or you divide into 2 for 3 level. And once you get these points, and from these points, you draw the lines parallel to the all sides of the hexagon, lines parallel to the all sides. If you see, this is the one side of hexagon, so you make these lines parallel to this. This is here, so you make these lines will be a parallel. If you are having this, you make the lines parallel to this, and then whatever diagram we can get, that will be a space vector diagram for particular multi-level inverter. So, and how we obtain the 27 number of the switching states. We compute this for one exercise. You can also do any one state, you can take and do the exercise. So any questions from your side? Hello, am I audible?
Yes, sir.
Yes, any question? How to draw the space vector diagram for any multi-level inverter? What is very basic? Divide this hexagon one side into a number of levels minus 1. If 3 level inverter is there, you divide DC link into 2. If 5 level is there, divide DC link into 4. If 7 level is there, divide the DC link into a 6. And just draw the lines from these points parallel to the sides of the hexagon. So that will complete the space vector diagram. And so any question? Is it clear how to draw the space vector diagram for 3 level inverter?
Yes, sir.
Yes, okay. So we'll meet tomorrow at 10:15. So any question? Okay, thank you. So we'll meet tomorrow.